Hi everyone, and welcome to this quick video where we're going to have a look through the next part of the topic and look at something called spectator ions. So this is probably an easier skill to kind of show than it is to kind of explain, so we'll just get started and work our way through. Before we do that, I just want to take a second to reintroduce and to make sure that we're clear about something called state symbols. So as you can see on the screen, state symbols are little letters that we use to kind of describe how we are finding the chemical in this reaction. So there are only 4 and we need to know them. So if you didn't know this, if you've come to this screen and it's new to you, it's definitely worth adding this to your notes and making sure that you've got this written down. Where we have S in brackets, that designates that a chemical is a solid. L in brackets is a liquid and G in brackets is a gas. And you should be able to see on the screen this kind of really curly looking L here. This is the one that you're most likely to see. So this sort of swooping L shape. That's just because depending on the font that's used when we print out a question, sometimes like the one that I've used in this one, an L can look a bit like a capital I or even a number 1. So they'll quite often use this really curly L here to designate something being a liquid. So keep an eye out for that. The last one that we use, so these are our 3 states of matter, solid, liquid and gas, but the last one that we use in chemistry is that quite often we take a chemical and we dissolve it in water in order to do a chemical reaction. Now to do that we use the symbol AQ. It's in solution, so we can't use S because S is solid, so AQ comes from the Latin and it's aqueous, which basically just means in water. Okay, so it's dissolved in water, so it's in solution. So the example you can see along the bottom of the screen, if we take table salt, so the stuff that you put in your chips, as its normal form that you're used to, it's NaCl with an S in brackets, so NaClS, meaning it's solid. If we melt it, so if we heat it up enough to melt it, it's NaClL. Okay, so that L in brackets means it's a liquid, so that's when it's melted down. If we boil it, so if we were able to get it hot enough to actually break all of the ionic bonds in that lattice structure and separate out all the ions, we would get to NaCl gas, so the G for gas. And more likely, if we were to dissolve it in water, so salt water, if you were adding salt to your water for making pasta or boiling potatoes or something, then what you've got is NaClAQ, this AQ in brackets. Now this becomes really important in the next bit of the topic that we're looking at just now for spectator ions, because what we are going to be doing is looking for changes, and we're also going to be looking for things that don't change. And something as simple as changing the state symbol of an ion can be enough for it to be a change. So when we're looking for things that don't change, we will be including the presence of spectator ions. Now just very quickly before I move on, the truth is you would very rarely, if ever, be asked to write down a state symbol. It does happen, but it's quite a rare question. It's more just that you're able to read a spectator ion and that you understand what they mean. So if you see them in a question, you don't need to panic. S is solid, L is liquid, G is gas, and AQ means in solution or aqueous. So let's get started thinking about spectator ions and ionic equations. Now I'm going to go through this with you in complete detail, showing you all the steps, but I'm going to make it really clear the bits that you actually need to be able to do. And it's not very much, to be honest with you. I quite like this bit of the course because the theory behind it may be slightly difficult to kind of implement or to really understand in detail, but what we actually want you to be able to do is really straightforward, really simple, which is quite nice. So when we take an acid or an alkali and we put them in water, they dissociate. Now we've met the word dissociate from before when we were thinking about water, and all it means is that the acid and the alkali chemicals break up into their ions. So your hydrogen ions, your hydroxide ions, and then any other ions that are there would be completely separated in solution. So they're free to move, which we learned earlier in the course means that they're able to conduct electricity. So some of these ions will react, but some of the ions that are going to be present during the chemical reaction do nothing. They don't take part. They are literally there as the reaction happens and they do nothing. Okay, so the term we use to describe those is a spectator ion. So the analogy that I always use, if you've been in one of my classes, you'll know that I am a bit daft on football. So one of the examples I use is that every Saturday I go to the football. Well, I call it football, but I go and watch a game, and my role in that process is a spectator. I am there, but that would happen whether I'm there or not. Okay, so I'm not taking part in the game. I'm not, getting to run on and score the winning goal, unfortunately. My job is just to effectively sit and watch. And in chemistry, some of our ions in these reactions literally do the same thing. So we call them spectator ions. So what we're going to do is look at some examples, and we're going to drill down into two different skills. The two skills you could be asked to do in an exam scenario. The first one is going to be just to simply identify a spectator ion, and the second one is to rewrite the equation without the spectator ions. Effectively a bit like a spot the difference. Cross out the things that are the same and rewrite everything that's left. So we'll go through some examples with you just now. So here's the full process, okay? And this is something that it's worth having down in your notes, the process that you would kind of go through to do this. But when I actually show you what you need to do, you'll see it's not particularly difficult at all. So ionic equations, similar to molecular equations, but the ionic compounds have been shown as individual ions. So we looked at ionic formulae for ionic compounds before. So ionic compounds would be split up into their individual ions. Everything would need to be shown, so all the formulae, all the charges, all the state symbols, everything needs to be shown. Now here's the good news. That will always be done for you. You don't need to do that step. You need to be able to understand what that is telling you, but you don't need to actually be able to write it yourself. So let's go straight into our first example. Okay, the example you can see on the screen here, sodium hydroxide plus hydrochloric acid gives you sodium chloride plus water. Now for each of those chemicals, we can write a chemical formula. So sodium hydroxide, we can do valencies and swap overs, so our SVSDF method. We can work through that for each of the four chemicals there, and we can get to a point where we have our chemical formulae. Now you can see we've also included state symbols here. Sodium hydroxide would be dissolved in water. It's an alkali, it's a solution. So is the acid. Okay, at the end of the process, you would have liquid water, and the salt would be dissolved in the water. So the salt in this case is sodium chloride. It would have the state symbol AQ, which you can see on the screen here. Now this is the step. The next step is the bit that I was saying to you. It's time consuming. It has a number of different steps, and it's something that we would never ask you to do in an exam for 4 different chemicals. We would only ever say to you, write the ionic formula, of sodium chloride or sodium hydroxide. You would have to do it once. In this type of question, there's so many to do that we would never ask you to do it all together. This is what you would end up with here. So the idea is that our sodium ion and our hydroxide ion have broken apart. So as soon as we have them in solution, what we know as a chemist is that all of the ions are free to move. It means that they're no longer joined together. So up here, we can think of them, if you imagine sodium hydroxide as a solid, sodium hydroxide, the sodium ions and the hydroxide ions will be locked together. But if we've got it in solution, this AQ, in truth, what's happening is the ions are actually floating about in the beaker, and they're kind of interacting with one another and floating around. The same is true for our hydrochloric acid. Our H plus and our Cl minus are separated. So whenever we have an AQ, what we're doing is we're splitting the ions apart. But like I say, you don't need to be able to do this. You would be given this line that you see on the screen here. So NaCl broken apart is Na plus and Cl minus. And you'll notice here that the liquid form here of water, it doesn't break apart, so we keep that as it is. We only break apart the ions with the little pluses in between to show any aqueous chemicals, anything that's AQ, because we know enough chemistry to know that those ions are just floating around. So what do we want you to do? Now that we've got to this stage, understand that or not at this point actually doesn't matter too much, to be totally honest. what you have to be able to do is to understand the idea of a spectator ion. So spectator ion, just like me on the Saturday at football, is something that is there but is not taking part. Now in chemistry, what that means is that the ions appear on both sides of the arrow exactly the same. Same charge, same state symbol, same everything. All we need to be able to do is to identify them, potentially cross them out, and rewrite without. So let's go through that. First question. You might be given one of these and simply for 1 mark in the exam asked to identify, it wouldn't even be the spectator ions, it would be identifying a spectator ion. You would get the mark for just identifying one of them. Let's go through it and find them all. So let's have a look at this equation here. If we have a look at this whole line on the screen, this one that I've got the red dot on the screen moving around just now, what we're looking for is anything that appears on both sides completely unchanged, exactly the same. So the first example is the sodium ion. So you can see the sodium ion here is Na plus Aq, and over here is Na plus Aq. That means that this ion here or this ion here, they are both examples of a spectator ion. They are the same ion. Nothing has happened to it during the reaction. In this question, you would simply underline or circle either of those, both of those. It's up to you. There's another one though. If we look closely, we should also be able to see that the Cl minus, the chloride ion, and the Cl minus chloride ion here, Aq, they are absolutely identical. So again, another example of a spectator ion, something that is unchanged from this side to this side. So the question might simply be, identify a spectator ion. You would circle any of the 4 things you can see circled on the board just now. The next type of example involves a little bit more work, but genuinely just a little bit more work. The other type of question that you could be asked to do, starting with exactly the same equation, so nothing different, having identified the spectator ions, so we can identify those, the next thing would be to rewrite the equation without the spectator ions. So what we're effectively saying is, that's great if we know that there are things present that have done nothing in this reaction. What actually happens in this reaction? So let's take them away and write down everything that's left. So we would write down this ion here, and this water molecule here, and it becomes this. So OH minus plus H plus gives you H2O. And that's actually the basis of what we've been doing so far in this topic. The hydroxide ion is present in a base, the hydrogen ion is present in an acid, water is present in a neutral. A base plus an acid gives you neutral. Now the beauty of this, and you'll see this yourself when you go on to do some examples, is it doesn't matter which pair of base and acid you use, you will always end up with the same equation left when you remove the spectator ions, because the only thing that changes when you change the base or you change the acid is the salt that you produce. We did naming salts in a previous video, but what we always produce is water. So if we were to do this example with potassium hydroxide and sulfuric acid, identified all the spectator ions, crossed them all out, what would we be left with? We'd be left with exactly the same 2 ions on the left, the hydroxide and the hydrogen, and the water on the right hand side. It won't matter because the spectators may change, but the actual chemistry of what's going on in this reaction stays the same. So let's look at one more example, because when we use a carbonate, something different happens. Same process, you could do the chemical formula for each of these. We've got calcium carbonate reacting with hydrochloric acid, giving us calcium chloride, carbon dioxide and water. Remember, acid plus metal carbonate gives us salt plus water plus carbon dioxide, so we've got 3 products. So there's our formula equation with all the state symbols present. Notice the G for the carbon dioxide because it's a gas, it bubbles off. Anything that's AQ, so this chemical here, and this chemical here are going to be split apart. Now what you'll notice is because this one is balanced, we've got 2 HCl. That means that when we break this one apart, we're going to have 2 of the hydrogen ions and 2 of the chloride ions. But like I said, good news, you do not need to be able to do the step shown on the screen just now. You need to be able to do the next step, which is, firstly, identify the spectator ions. So you would need to identify one single ion in this whole line that appears exactly the same on the left-hand side and the right-hand side of the arrow. No difference in its state symbol, no difference in its formula, no difference in its charge. Really straightforward. So, calcium ion, Ca2 plus Aq, appears on both sides. Chloride ion, 2Cl minus, aqueous, appears on both sides, completely unchanged. The other type of question, let's just move on. The other type of question, exactly the same again, starting with the same thing, identifying the same spectator ions. We now rewrite the entire equation without the spectator ions. Again, just like before, it doesn't matter whether it was calcium carbonate or copper carbonate, whether it's hydrochloric acid or sulfuric acid, you will always end up with the same final reaction here if it's an acid plus a metal carbonate, because the base plus the acid are going to make something neutral. So that is spectator ions. That is a kind of a run through of how that works. You're hopefully going to be able to do some examples of that as well, and to have a go at doing some examples yourself. Make sure that you've added these into your notes, that you've gone through the process of writing it down, circling or scoring through spectator ions, that you understand what the state symbols are, and that you understand that a spectator ion has to appear identical on both sides of the reaction, so both sides of the arrow. Okay, I hope you found that useful. If you've got any problems at all, obviously reach out to your chemistry teacher and ask for help, but hopefully you found that a useful video going through the chemistry of spectator ions. Okay, have a great day. Thank you.